First of all, I would like to thank my co-authors and also the Spanish Ministry for funding this work. This talk has been divided into 6 sections. A brief introduction would be made first, and then try to show how the kinetic and the infrared spectroscopic experiments were done, the methodology and the experimental setups employed for this study in order to estimate the atmospheric lifetime and the global warming potential of 3,3-difluoropropene, referred to as HFO 1243 ZF, and to finally conclude if this HFO is a suitable alternative to HFCs. So as you all know, CFCs and HCFCs are responsible of the depletion of stratospheric ozone layer. This depletion is caused by chlorine atoms released from the photodissociation of these species. And since the Montreal Protocol, many efforts have been made to reduce the emissions of these species by restricting the consumption and their production. In this figure, you can see the phase-out timeline and some actions suggested by the Montreal Protocol and the US Environmental Protection Agency. And as can be seen, CFCs were restricted, the consumption stopped in 1996, while HCFC's consumption was gradually decreased or banned. To reach 2030, which is the date, all HCFCs will be phased out. In the meantime, many other alternatives were proposed. For example, the second generation of CFC replacements, the hydrofluorocarbons, were suitable when were proposed for replace CFCs and HCFCs in many industrial applications such as refrigeration or air conditioning. And the problem with these HFCs is that even though they are ozone-friendly substances, they do not deplete a stratospheric ozone layer. They have a high contribution to the global warming of Earth. The parameter that quantifies this contribution is the global warming potential, GWP, which is a measure of the total amount of energy that a gas absorbs during over a particular period of time. In this case, this diagram bar shows the global warming potential for 100 years. So, what we want to know if this contribution is high or not. As can be seen here, HFC's global warming potential are lower than CFC's, but still they are very high. How can we calculate global warming potentials? As you can see in the equation, this expression, it's a relative measure, a relative parameter, which compares the instantaneous relative forcing of the greenhouse gas relative to that of CO2, is this denominator in the equation. Also, another parameter, important parameter to quantify the global warming potential is the atmospheric lifetime of the species, or what is also called the residence time. So these two parameters highlighted here can be obtained from experimental data, as I'll show you later on. An example is, and you will see how I choose this HFC. This HFC 134A has a global warming potential of 1,430, to be precise, which means that the HFC is 3 orders of magnitude more efficient trapping heat than CO2. It's a very powerful greenhouse gas. So we want to look for a low global warming potential alternative to these HFCs. How are we going to look for? So we can find, or we can look for, we can search species with low radiative forcing, which means low infrared absorption, or species with a short atmospheric lifetime. In other words, species which are quickly removed from the atmosphere. So experimentally, we need to know the molecular radiative properties of the gas by measuring the infrared spectrum, and the rates of all the potentials removal processes of these species in the atmosphere, especially the reaction with the main oxidant in the atmosphere, the OH radicals. One of the most recent HFC proposals to replace HFCs is the hydrofluoroolefin family. In particular, I'm going to focus on HFO1243ZF, which is a potential replacement for the HFC134A that we saw that it presents a very high global warming potential. So before the widespread use of this HFO as a replacement in automobile mobile refrigerant, we need to predict the atmospheric impact of these species in the atmosphere. For that reason, the purpose of this work is to determine the reaction rate coefficient for the OH reaction under several temperature and pressure conditions, those of the troposphere, the lowest region of the atmosphere, which range from ambient temperature. You know that depending on the latitude, altitude, seasonal, the temperature can vary, up to the tropopause, where the temperature is around, on average, 220 Ks. Also, the gas density, the pressure in the troposphere decreases quite fast, from 1 bar at sea level up to, or down to 200 millibars at the tropopause. And the second objective of this work is to determine the infrared absorption cross-section that will allow us to calculate the global warming potential. For the kinetic measurements, we used this non-commercial commercial experimental system which consists in you can see here several lasers. This one is for photolyzing a suitable precursor to get or to obtain OH radicals in situ in the center of this reactor. And then the OH in the ground state is excited by this other laser at 282. And the off-resonance laser-induced fluorescence is monitored as a function of reaction time. This LIF intensity behaves like I'm showing here. The behavior is well described by a single exponential function. So from the fitting of these curves, we obtain the pseudo first order rate coefficient for a given temperature, pressure, and HFO concentration. If we vary the concentration of our reactant, HFO, we see a linear relationship between the pseudo-first order condition, the pseudo-first order rate coefficient and the concentration. From the fitting of this straight line, we get from the slope the bimolecular rate coefficient at that temperature and pressure. The ranges of temperature and pressure we used in our study are those shown in the slide. For the pressure, we vary from 50 to 650 torr, and for the temperature, range from minus 10 Celsius degrees up to 885 Celsius degrees. Here I'm showing just an example of how the rate coefficient varies with temperature for a single total pressure. And as you can see, the rate coefficient is decreasing when temperature is increasing. So that is called negative temperature dependence. This trend is observed at all temperatures measured, and also the value, the order of magnitude of these rate coefficients, 10 to the minus 12, indicates that the reaction with OH is fast, is quite fast. That's the range. Here in this figure, in this plot, you can see the average rate coefficients of all measurements made as a function of total pressure. If we focused, for example, at one fixed pressure, here at a single temperature, we can see how the rate coefficient is increasing when the pressure is also increasing. So it's a positive dependence, and this dependence is well described by the Troy expression that I'm showing here. You can see that this is not a linear relationship, it's a more complex more complex equation to fit. It's a nonlinear fitting. And we can see in this expression how this rate coefficient K can be simplified depending on the conditions or the regions of these curves. For example, we can define the high pressure regime where the rate coefficient is almost constant, and the rate coefficient is called the high pressure limiting rate coefficient. This rate coefficient is also dependent on temperature. As you can see here, 3 examples for 3 temperatures. And if we move downwards at the low pressure regime, the rate coefficient is linearly dependent on the pressure, that is the concentration of the gas bath employed. In this case, helium. We used helium. So in this case, the dependence of the rate coefficient with helium concentration is linear. And the proportional constant is what is called the low pressure limiting rate coefficient. From the fitting of these curves, we can obtain the low and high pressure limiting rate coefficients at different temperatures. And the temperature dependence is given by these 2 expressions, and we can see these 2 constants, m and n, which are positive in our case. So that means that the temperature dependence for the limiting rate coefficients are in the same trend that we observed for the rate coefficient. They increased where the temperature decreases. In the intermediate region, what is called fall-off region, we cannot use any of the simplifications of the Troy expression. We need to use the whole or the complete expression. But we know all the parameters inside, so we can use these temperature and pressure expressions to derive any rate coefficients under any temperature and pressure conditions in the troposphere. As an example, I'm considering just a middle latitude troposphere. You can see in the poles and equator, the troposphere, the thickness of the troposphere is different. So here, the rate coefficients at temperature and pressures, those for the tropopause, mid-troposphere, or ground level, is roughly the same, is quite similar. So we can conclude that the HFO is reacting with OH similarly throughout the troposphere. So for that reason, we used the mid-troposphere data, this rate coefficient, to estimate the atmospheric lifetime of this HFO. The Intergovernmental Panel on Climate Change defined the atmospheric lifetime as the time required to turn over the atmospheric burden. That means that it's essentially a scale factor relating a constant emission to a steady state burden, or an emission pulse related to the time integration burden of that pulse. But often the lifetime, or the atmospheric lifetime, is assumed to be a constant and independent of the sources of emissions, and it's also taken as the E-fold decay time. So assuming that, or considering that assumption, the atmospheric lifetime of HFO can be estimated by using this expression. So it's the reciprocal of the rate coefficients at certain conditions of temperature and pressure. As I said before, I used a mid-troposphere in middle altitude. And also we need to consider the average radical concentration in the atmosphere for OH is 10 to the 6 radicals per cubic centimeter. And that gives us the atmospheric lifetime around 1 week. So 1 over E times is reduced the initial concentration of this species in the atmosphere. So it's removed quite fast. If we take into account the horizontal and vertical transport timescale, we can see how this HFO will survive latitudinal long-range transport, and it won't be transported to the stratosphere because we need more than several months to cross the troposphere and reach the stratosphere. Well, so this species is a short-lived species. We'll see what happens with the molecular relative properties of this, because we need to know also which the infrared spectrum is to calculate the radiative forcing of the species. So for the infrared measurements, we used an experimental system, which is here sketched. And it consists in a Fourier transform infrared spectrometer coupled to an absorption gas cell of a single path of 10 centimeters. And the spectrometer is equipped with a liquid nitrogen mercury cadmium telluride detector, which permits to measure the transmitted intensities, both in the presence or absence of absorber, between 500 and 4,000 wave numbers. So a very quite big range. Here I'm showing an example of the infrared spectrum of HFO in terms of the absorbance that we can calculate it with the transmitted intensities, I said before. So we can see how there's no, or almost negligible absorption from almost 1,500 wave numbers up to 4,000. So this region is not important for from the atmospheric point of view. But here in this fingerprint region of the infrared spectrum, we see some strong absorption here at 1,171 wave numbers, which corresponds to the CF stretching vibrational mode of this mode. Okay, so if we record this infrared spectra as a function of HFO concentration, we can determine the infrared absorption cross-sections, sigma, from the slope of the plots of the absorbance against the HFO concentration. Of course, we need to take into account the path length of the gas cell, that it's 10 centimeters. In this case, the infrared absorption cross-section for that peak absorption is on the order of 10 to minus 18, which is a very strong infrared, strong absorption. Here, if we delete the non-absorbing region of the spectrum, we can see in terms of the absorption cross-section, the spectra, and we are interested just in the atmospheric infrared window, which is located between 8 and 14 microns. So we want to determine here in this region the integrated absorption cross-section, not the absolute as is showing here, but just measuring the integrated absorption cross-section every 10 wave numbers. I'm going to show you just in a moment why we use these 10 wave numbers intervals. So we need to integrate it up to here. So let's go back to the definition of global warming potential. Up to now, we know the atmospheric lifetime of CO2, which is in the literature, its radiative forcing, and we've calculated or estimated the atmospheric lifetime in years for the HFO is almost negligible, 0.02. So we need to calculate the radiative forcing for HFO. This radiative forcing is a measure of the influence of a greenhouse gas emission on the net change in Earth energy balance. In other words, this radiative forcing can be approximately calculated by this summatory of these two terms. This is the radiative forcing per cross-section unit, which is tabulated every 10 wave numbers. That's what we needed to integrate our infrared absorption cross-sections every 10 wave numbers. So the integrated infrared absorption cross-sections are determined using the same procedure as before for the absolute infrared absorption cross-sections, using the Beer-Lambert law. In this plot, I'm showing these two terms of the summatory separately. In red, we see the integrated infrared absorption cross-sections. And in blue, you can see the radiative forcing per absorption cross-section unit. I'm also presented here different, the main absorbers in the atmosphere, ozone, water, and methane, and CO2, of course, ozone, to see how this radiation is decreased by the absorption of these species. Here we can see the peak absorption for the HFO is here, where there's some light available to be absorbed. So we use the expression I showed before. We get a radiative forcing of 0.21 watts per square meter. If we take into account the atmospheric lifetime estimated from our kinetic measurements, we get a global warming potential for a time horizon of 100 years of 9. If we remember the global warming potential for the HFC proposed to be replaced, this is HFC 1, 2, no, it's not 1, 2, 3, 4. The one number is off. It's only, I think it's 1, 3, 4A, the HFC. It's almost 2 orders of magnitude lower than for the HFCs. So something is improved. So to conclude, we can say that the main atmospheric degradation of this potential emission, because now there's no emission of this hydrofluoroolefin, would be the reaction with OH radicals. It would be very fast removed from the troposphere with a short lifetime of around 1 week. And the radiative forcing calculated is much higher than that for CO2, but because of the short atmospheric lifetime presents the HFO, the global warming potential is almost negligible compared to the HFC. So finally, it seems that HFO 1243ZF is a good candidate to replace the HFC 134A said before. And that's all. Thank you.